Good evening, ladies and gentlemen, and welcome to another edition of the Windsor Park Climate Conversation, brought to you by the Windsor Park Neighborhood Association. My name is Martin Lukey. I am chair of the Climate Committee, and tonight we have an episode that everybody has been talking about, although you don't know we're having this episode. We're all talking about extreme weather, and that is our show. Extreme Weather and the Consequences of Climate Change is the actual title. And it is quite obvious now that our weather is crazy. And we've brought on a couple of panelists who are real experts on the subject. And we're going to have a frank conversation about what's actually happening. I would like to introduce my co-conspirators on the show. My co-host, Barrett Selwyn, and also our intrepid director, Selwyn. Thank you, gentlemen, for joining the show. Barrett, who's our first panelist?
So our first panelist is the esteemed Dr. Justin Schoof. He is director of the School of Earth Systems and Sustainability at Southern Illinois University, also professor of geography and environmental resources. His research interests include climate variability and change, synoptic climatology, and statistical climatology. He has a doctorate in atmospheric science, so you can see he's right on topic for this evening's show. Yeah, Dr. Schoof, welcome.
Thank you so much for having me. Glad to be here.
Our other panelist is an Austinite and a former storm chaser from the 70s. His name is Bruce Melton. He's a professional engineer, environmental researcher, filmmaker, climate science education specialist, author, and director of the Climate Change Now initiative, founded in 2005. He has written over 600 reviews of academic climate science and lectures regularly. Bruce, thanks for being on the show again.
Thanks for having me.
All right, gentlemen, let's get to it. So July turns out to be the hottest month in history, apparently for the last 120,000 years, according to one article that I saw. And I'm curious, Dr. Schoof, is that actually accurate? Is that true?
Well, it's that's kind of the extreme version of the statement, right? So we know that we know it's the hottest within the last 120 years or so of good measurements, and it's not even close. We are about 1.2 degrees Celsius in July above the 1951 to 1980 average. So if you're thinking in degrees Fahrenheit, we're about over 2 degrees Fahrenheit above that long-term average. So the July global temperatures were literally off the charts. Now, when we say maybe the longest in the last 120,000 years, what people are saying when they make that statement is that we know that we're the warmest that we have been, in at least a couple of millennia, probably considerably longer than that. But when you make that 120,000 year statement, what you're saying is that the evidence that we see in ice core data doesn't suggest that we've been this warm over that period of time. Now, what we know, I think everybody in this room already knows, and hopefully what the listeners will take away, is that extreme events are really most commonly combinations of several factors that come together, right, at the same time. And so what we're seeing with climate change is that we've got this extra element in there. And so sometimes you hear people make probabilistic comparisons, like, for example, maybe an event like this is double sixes, right? But what we've done is we've taken one of our dice and we've changed 3 of the faces to a 6, right? Or something like that. So that what we're really doing is increasing the odds of that event occurring. And so I think a lot of our climate extremes fall into that space. I don't think we need to go back 120,000 years to be really concerned. And some people would say, a critic would say of that statement, Well, we really don't know about the day-to-day variability over that 120,000 year period. We really only know about the average. And what we're seeing now is that, variability is really where the extreme events lie. They move upward with the average, right? As the average increases, the extremes increase too, in just about every variable you can think of. But it's very hard to make a definitive statement about 120,000 years, but it's scary enough to see how badly this record was broken just in our observational record. So that's without looking at any paleoclimate data or any proxy data, just focusing on actual observations. We know that this was a very extreme event.
And that was probably because of El Nino coming back around.
Yeah, well, certainly, something very interesting happened, which is that we've been in a La Nina state for the last several years. And what happens in a La Nina is that you tend to get a lot of warmth in the extratropical oceans, right? And so what happened is that we now have flipped over.
Extratropical meaning not
meaning
tropical?
just outside of the tropics, right? The mid-latitude oceans really is what I'm referring to. And so, what we had then is a flip over to El Nino. And then El Nino warms the tropics, but the signal to the extratropics is delayed a little bit. So what we had is a really warm tropical Pacific that we get with El Nino, but we had the remaining warmth from a triple La Nina, 3 consecutive years of La Nina, still retaining some of that heat in the ocean in the extratropics. So you had this kind of double whammy. And so, I've heard a lot of people say, for example, that El Nino is responsible, right, for the record warmth that we're seeing this summer, but I disagree. El Nino is responsible for the anomaly, but our emissions and climate change is responsible for the underlying trend. If this El Nino had occurred 30 years ago, it would be much lower on that trend line, and we wouldn't be seeing the absolute level of heat that we're seeing now. Again,
so if this giant heat is like a huge, horrible home run, if it hadn't been for climate change, it just would have been a regular long fly ball, so to speak.
Right. Well, I mean, we can think about this a little bit differently. I'm sure that you all heard after the large 1998 El Nino for about 10 years that global warming had stopped. That was a very common message that we heard after the 1998 El Nino. The reason is because 1998 at the time was like the summer of 2023 when you looked at it on the chart. Look at 1998 next time you look at a figure that shows the annual temperature time series. It's incredible. Interestingly, now 1998 is not even in our 10 warmest years on record. And the reason for that is that we have this incredibly strong upward trend. Now, interestingly, we can give a little bit of a prediction. We normally don't get the greatest atmospheric warmth during the early part of an El Nino, which is where we are right now.
Oh boy.
So we know that El Nino is a major contributor to a lot of the events that we've experienced this summer. But we really expect that even though I think 2023 will be the warmest year on record, 2024 is also likely to be a contender because an El Nino is sometimes more than 1 year. It can be a couple of years in duration. And so as that goes on, we'll get more warmth in the atmosphere really, this winter and then, into the first part of 2024. So we've probably got a lot more to hear about with this El Nino. But one of the things that I wish that we were hearing a little bit more about is the fact that it's really this El Nino occurring on top of a long-term upward trend in temperature.
Let me add 4 points of discussion to this. Air pollution regulations in China, India, and shipping are reducing sulfate emissions. Sulfates are cooling aerosols. About half of warming to date has been masked by cooling aerosols that are emitted from fossil fuel production alongside of carbon dioxide. So now China, India, and shipping are reducing those sulfate emissions. This started a couple of years ago. We've got quantification on shipping now, which is the average when shipping regulations are fully enacted, about 0.16 C of warming that is unmasked because of the reduction of these cooling sulfate aerosols. We don't have, go ahead.
Just to make sure I'm catching up with you, Bruce, you're about halfway through that when the irony dawned on me. If I'm understanding you right, these sulfate emissions are supposed to be bad in the first place. They're pollution already. You're saying that India and China and the big shipping tankers and ships, they're all doing good pollution reducing compliance to these new rules now. But then the side effect of less pollution is this particular kind of pollution, even though it's bad for other things, still was actually was reducing the global heating a little bit. And now that, if I'm hearing you right, then taking it away is making the climate change worse. Is that
correct? James Hansen, the 32-year director of the NASA Goddard Institute for Space Studies, retired now, calls it a Faustian bargain. He's called it this since 2008, I believe, where you eliminate emissions from fossil fuels. You get this, it is a short-term phenomena too. It's 10 years plus or minus, but you get this warming from what you were doing to create cooling or create less warming.
I would like to point out, if I could, that we find these kinds of conundrums in many aspects of sustainability. For example, the United Nations has 17 sustainable development goals, which I would encourage listeners to become familiar with. These are all things that will make our world a better place if we strive to meet them. However, they are presenting extra challenges. So for example, one of them is to bring people out of poverty, right? To eradicate poverty. What a great idea that is. Of course, we're all in favor of that. But the reality is also that when people come out of poverty, they emit more carbon. The carbon footprint grows. I mean, it's a guarantee. And so that's not to say we shouldn't bring people out of poverty, of course. What it means is that if we want to bring people out of poverty while meeting climate goals, we have an additional challenge. Right? This happens all over the place. So the IPCC has actually done some work on those sustainable development goals and trying to understand how different sustainable solutions might work with and against those sustainable development goals. And so it's very interesting to think about those trade-offs. And Bruce is entirely correct that reducing sulfate emissions is a really good idea because it will improve air quality, reduce acidic precipitation. There's some real benefits of that. But at the same time, once you remove that, you're actually reducing something that's actually helping to keep us a little bit cooler at the moment for the wrong reasons. By the way, more broadly, this has even bled over into geoengineering conversations, whereby people have said things like, let's pump the stratosphere full of aerosols to stop warming. It's a terrible idea for many, many reasons that we don't have to go into here. But certainly we understand there's some big uncertainty bars on the effect of those aerosols, right?
But clearly the solution is to send everyone into poverty, and that'll solve all our problems, right?
Very reasonable, Selwyn.
I've got one more. I had 3 things that were causing warming in addition to a little bit from Nino and climate change. The 4th is a mind blower. Do y'all remember the Tonga eruption in January of 2022? The undersea eruption that injected so much water vapor into the stratosphere that it's a volcanic eruption that warms. It doesn't cool. Volcanoes usually have sulfates. that create this geoengineering, sulfate emissions into the stratosphere that cool the planet. This volcano did not. And a minute ago, I misspoke. I said 0.16 warming when the shipping quantification was when all the shipping regs, when those were all fully implemented. That's 0.1 C. The Tonga eruption, it's probably fully realized now. That's 0.16 C of warming, average, the middle. It's a range of error bars. But really, really wild thing, a volcano that creates warming. And it's because of all that seawater that got injected into the stratosphere.
Yeah, I would like to comment on that too, if I could.
Sure.
So the result on the effect of that warming from that eruption is based on a couple of modeling studies that have been done. And there have been a couple. This is very fresh science. So we really don't know a lot about it. But I want people to be careful because one of the things that's going to happen, I've actually already seen it starting to happen, is that we're going to see a concerted effort to blame recent warming on the water vapor from this eruption. And I want to reiterate, Bruce said about 0.16, okay? We get about 0.11 or so from the 11-year solar cycle, and we don't even notice it, right? So
these are all fractions of a degree of Celsius.
That's right. So we're talking about less than 0.2 of a degree Celsius, which is really lost in the interannual variability from things like El Nino and La Nina. So I just want listeners to be careful about letting people convince them that the Tonga eruption is somehow responsible for this summer's extremes and that humans are not. That would be the wrong conclusion to draw from the science on Tonga.
All on top of Justin, can you answer me a question? The academic work that talked about this said that these impacts, this warming, will last from 5 to 10 years. Why does water vapor last longer than sulfate? Sulfate's a couple of years in the stratosphere mostly.
Water vapor survives in the stratosphere because you get oxidation of methane there, and water vapor is a byproduct of that. And so you've always kind of got some water vapor. Also, one of the things that happens in the troposphere, of course, is that you've got the hydrologic cycle pumping water through about every week or so. Water doesn't last very long. It just keeps cycling through, unless it gets into the deep ocean or something, and then it's going to be down there for 1,000 years maybe. But water in the troposphere gets cycled out really fast. This is the same reason that volcanic eruptions have to get material to the stratosphere to matter. So we've had some very large eruptions historically, like Mount St. Helens, for example, produced a huge ash cloud, but it was kind of a blowout of the side of the mountain, so it didn't really produce a stratospheric injection, and therefore it had very little effect. On the other hand, we've had some really incredible volcanic eruptions in history. The Tambora eruption in 1815, I guess, or 1816, produced what's sometimes referred to as a year without a summer, because we had snow in New England in the middle of summer and frozen streams and things like that, crop failures and that sort of thing. So these large volcanic events do happen. And when you get a large volcanic event that produces a large warming, that's usually maybe a 5-year signal or something like that too. It doesn't stick around very long. The last one that we had that was really large in the system was Mount Pinatubo in 1991. And that cooled the Earth by about 0.5 degree Celsius. And you can see that in the temperature record. But then after just a year or two, you can't even tell it happened. And that's because the stratospheric aerosols actually will then slowly settle over settle gravitationally over a few years, and their effect goes away.
So these are pretty big effects, but despite these sort of big historical examples, you were pointing out earlier, we are, like in July, we had by far the hottest month, or by far the hottest July ever. And I remember I've spent most of my adult life in Windsor Park, but recently I have moved for the year to South America. I'm actually in South America right now in a place that got relatively little of the current heat wave, luckily. But I read that elsewhere in South America, where it's normally winter right now, there a couple weeks ago, they were absolutely smashing heat records and having summer type temperatures in the middle of their winter, even in the places that usually had, real winter, very cold winter. How extreme is this? What, as a scientist who studies weather extremes, how do you define extreme weather, and how does the recent how extreme is the recent South American summer instead of winter heat wave?
Right. I think it's quite extreme. But when we get into questions of extremes, we have some issues, frankly. We have issues with data records. So there's some interesting things you can do. For example, if you have a 1-year record, a 1-year series, you're guaranteed a record. If you have a 2-year series and there's no trend, you have a half a chance of a record in your 2nd year, and a 1/3 of a chance in your 3rd year, and a 1/4 of a chance in your 4th year, or whatever. So we can figure out, if there was no climate change and all the series were flat, right, then what would we expect in terms of records getting broken? And the reality is we're seeing records getting broken a lot more frequently than they should if there were no climate change. So there's very clear statistical information. Now, you hear people talk about like standard deviations a lot. So people will say it's a 3 sigma event. That means it's 3 standard deviations above the mean, right? And a standard deviation could be thought of as like the average deviation from the average. Now I'm talking a lot of jargon, but what I'm really saying here is that the more standard deviations you are above the mean or below the mean, the more extreme an event is. One of the problems with that approach is that it makes the assumption that the distribution has the same shape on both sides, and that it's smooth, that it's a normal distribution, a bell-shaped curve. And many of the extremes don't behave that way. So when we say something's a 5 sigma event, that's really extreme, but it's more extreme if you're thinking about it as this nice symmetric distribution rather than thinking about it with its true statistical form, which we don't know because we don't have the data. So when we think about how extreme events are, that's one instance in which we can really use climate models to help us. So one of the things that climate scientists do is we can run a climate model just using the known natural drivers, right? So we know where we are in terms of Earth-Sun geometry and all those things that affect climate over long time scales and, things like that. But then we can also run the model with land use change and carbon emissions and, all of the things that we've done. And, when you do that, you see 2 completely different spaces. And so this is one of the kind of state-of-the-art approaches that's being used for extreme event attribution. And so when I say attribution, what I'm saying is when an extreme event occurs, can we attribute it to humans? Can we attribute it to anthropogenic forcing? And what you see is that when you do these kinds of studies, you do long integrations usually. So you might run your climate model for 2,000 years under each case. And then that gives you these extreme events that you need 2,000 years of natural climate to produce this really large event. But when you get an extreme event, you can say, this happened 5 times as frequently in the simulation with elevated CO2, right? And so it's not a definitive attribution statement, but it allows you to say, indications are that climate change played a large role in that. And so if I go back to one of the things that I said earlier, it's important to realize that climate change is one factor in most of the extreme events that we experience. And we know this because we know that extreme events also occurred before we had this large effect on the environment, right? So for example, there's a whole field called paleotempestology where they study hurricanes in the paleo record. And it's really fascinating stuff. So we know that these events were happening back then. So what we're really interested in is thinking about how they've changed, right? And what our role is. So just as we can't say this climate change event, was absolutely definitively caused by us, it's equally impossible to say that we played no role, right? So when we think about these climate events, extreme weather events, we're in a system now that we've influenced so much that it would be very hard to discount at least some role of climate change. And I'd be very interested, if people are interested, in talking a little bit about like recent events like the fires in Hawaii, for example, which
I bet we do have readers who are interested in that. They may have other questions as well, because you've already covered a lot of things. I want to urge our viewers on the live broadcast to make comments on YouTube. We do have a volunteer, not just someone, but another volunteer, Jose Munoz, who is monitoring those comments, and we'll pass your remarks on. We'll try to get your questions on the air if you have any. So I just want to urge viewers to participate. And please tell us, how we can, what kind of approach we can take to where's climate change versus the horrible fires in Maui.
Right.
Can I just interrupt for 1 second?
Please.
Someone did ask a question, but I've asked a clarifying question from them. So Anthony, if you want to please clarify your question, that would be helpful. Then we can ask it on the air.
Thanks, Owen.
I'm very curious about this phenomenon of storms over the last few years getting bigger. And I remember it was, I think, a hurricane that occurred a few years ago when we suddenly had a whole bunch of hurricanes occur one year, and they just kept coming and kept coming and kept coming. There was an image of the map of the United States, and the storm literally stretched from Houston to New York City. And it was the first time I'd ever seen a storm that was actually that big. And that's what I think we're talking about when we talk about climate change possibly affecting weather, is that maybe, right now we haven't had as many hurricanes as before, but sometimes when we get them, they are gigantic. And Bruce, in your experience of storm chasing, what do you see in that regard?
Absolutely. Hurricanes, for a while, the data on hurricanes was inconclusive. The Atlantic hurricane storms were getting, the more extreme storms were getting more extreme, but in the Pacific, they were not. Pacific gets a lot of hurricanes. Now across the globe, we've got an increase in extreme hurricanes, Cat 3 and Cat 5. That is, I believe, about 60%. I've got it in one of my slides if we want to look at that after a while. Pull
it up now, Selwyn. Next slide.
Let's see. Share. It's this one right here. There's Climate Discovery. Y'all visit Climate Discovery. There's a gratuitous pitch for my latest film. Won 2 awards from climate change impacts from Padre Island to the North Slope of Alaska. Let's see. We were going after hurricanes right here, 50 years ahead. And I've actually got, this is not really for public consumption, but it's just kind of to show the amount of work that went into looking at how I interpreted that hurricanes are getting stronger faster than projected. And so
when you say 50 years ahead, you mean we're 50 years ahead of the predictions of stronger hurricanes?
Correct. Hurricanes today are as strong as projected for 50 years in the future.
This is projected from when, Bruce?
Well, let's see. It's just, sorry. I don't think I can conveniently increase this so I can read it. Um,
I have a graphic of all the hurricanes that have struck the US. If you want to see that, if that would be interesting. I'm not sure it's going to.
yeah, this paper by Knudsen specifically says up to 60% increase of Cat 3 to Cat 5 storms globally. So we've gone beyond the Atlantic Basin versus the Pacific Basin as of 2020. And sometimes these projections require some pretty deep interpretation. Sometimes one paper that tells us that what this scientist is reporting on is happening X number of years, decades ahead of previous projections.
Wow.
Well, that falls right into line with what we're all seeing. And I think we all can agree that after looking at so many models over the last decade or two of climate change, all of the models seem to be coming true, except for one factor, and that is the speed at which it's going to occur. And we're learning now that it's happening a lot faster than they were originally predicting. And so that's kind of what we're looking at as climate change is getting more obvious and showing up in the news, as opposed to just in the weather part. The weather, when the weather becomes news, we've got an issue. But Dr. Schoof, is it showing up in your research that this is all happening faster than predicted?
Yeah, so there's a couple pieces of this that I want to comment on. So the first thing is about the intensity and the destructiveness of tropical cyclones. This is an interesting point because we've known, Kerry Emanuel at MIT published a paper in the mid 80s, like I think 86 or 87, where he showed theoretically that we should be seeing an increase in the intensity of tropical cyclones with warming. So the scientific community has at least known that there's a theoretical basis for that for a long time. And so it's one of these things where there's a question about whether or not we've been able to detect it, right? And so I think what we're seeing now in some of the studies that Bruce is referring to, they're showing things like slower moving tropical cyclones, right? So this Harvey that you guys know all about, Harvey is a great example of that, a really slow mover. And so there's been some indication that tropical cyclones are moving slower than they used to. And so that's going to increase the rainfall rates and we'll have more flooding catastrophes, even if they stayed at the same intensity. When you add the increase in intensity with that, then you start to really see the heavier impacts. Referring back to your initial question about the size of these systems, I haven't seen anything indicating that tropical cyclones are growing larger, but it's important for listeners and viewers to know that the size of the hurricane doesn't matter. It matters in terms of the spatial extent of the impacts, but it doesn't relate to intensity. So you can have really large hurricanes that are kind of weakish, and you can have really small hurricanes that are very strong. So you don't want to make the assumption that a larger hurricane is a more intense one, right? The size that you see on a satellite image is about the cloud shield in the upper levels of the hurricane and all of those kinds of things. So I would just encourage some caution, drawing that parallel.
One of the challenges with large storms, then, like Sandy, when Sandy made landfall, it was not a hurricane anymore, but it had extremely widespread destruction because it was an enormous storm. Ike was another one. Ike made landfall as a 2, but it had a Cat 4 surge. And
we had trees down in Illinois from Ike.
That's insane.
Big. And
that's 1,000 miles away.
Yeah, it's pretty amazing.
It's one of those things that's just going to take some more time to say whether or not they're actually getting bigger or not, but you can certainly have extraordinarily extreme storms that are very small.
The other thing that, something you just said caught my ear, and I think it's important to mention too. As Hillary was barreling towards the Baja Peninsula and then Southern California last week, or over the last week, I should say, there was some communication that it had been downgraded. And that was not good communication, because it remained an extremely dangerous storm for people that were in its path. So when you say that something's downgraded, I know they meant that in a scientific sense, but the public may view that as that the threat is not as severe. And so that kind of language can actually cause some problems.
So it's good that you're explaining some of the details of how, what different terms mean to different people. I'm a little concerned that, some things are sort of more or less unfiltered within I guess, the scientific discourse, but sometimes there's still influences on this discussion that are really from outside forces outside of science, more like, politics or people trying to affect how people see issues. Martin, am I remembering correctly? We're blessed with a couple of very good panelists, but we didn't get all the ones that we were originally seeking. Is that correct?
Yes, that's a good point to bring up. The original idea was to get a local Austin TV weatherman to make an appearance alongside this panel, so that we could have kind of a person who's doing weather every single day and have their opinions. And it turns out that in Texas, it's kind of politically inconvenient to talk about climate change, depending upon what job you have and who you're working for. And one of the people that I did some outreach to works for LCRA, and it turns out that he really wanted to be on the program, but he was told he couldn't. And so the irony is that in this place where we have a really extreme weather, some people are not allowed to actually talk about it in terms of climate change. They can talk about it in terms of what the weather was that day, but they can't have any kind of overall other opinion on that idea. And so, we find ourselves wondering, if there's some truth that's being hidden sometimes in this reality of how it is we interpret the news. And that brings me also to this other idea of what happened in Maui, specifically this headline grabbing story of the fires there. And in the subheadline is that they're mentioning climate change immediately, and they're not waiting to get it into the body of the story. They're putting it up at top. And that's still, to me, a little questionable if climate change was to do with that, or if it was just bad human management in terms of this particular story with the grasses that were there, and the potential for the electrical system to have really been in a position where it creates sparks. And so I don't know, and that storm being the hurricane being involved with making the wind and creating that situation. How Bruce, how do you read that? Have you been looking at that?
Let me pull up another slide. And that the fires on Maui. Here we go. The fires on Maui are very similar to our Bastrop Complex fire we had here in 2011. And just maybe let me back up just a minute to preface everything. You see here, I say Central Texas notable climate change caused extremes. It's two things. I can say that because I'm an engineer. I'm an applied scientist. I apply science to life so that we can be safe. I can take liberties with labels where I say caused. I can assume that it's 50, 60% caused by climate change. I can say caused. scientists have statistical norms that they have to follow to say caused, and generally they won't say caused. They'll say likely, very likely, probably, etc. So that's one thing. The other thing with this, with any extreme, is generally there are multiple causes and multiple human caused reasons why the extremes happen. And I'm talking about big events, not just heavy rain. I'm talking about these events that I've listed here. And so, okay, so there's many different causes. Let me get back to Maui and the hurricane and the firestorm and the Bastrop Complex fire in 2011. In 2011, we had a tropical storm that went into the Texas coast, at the Texas-Louisiana border, and created a 30-mile-an-hour steady wind out of the north in Austin and just to the east of Austin. That wind clacks some power lines together, sparks, big wind, big fire. 1,400 homes were burned. The biggest fire in Texas by an order of magnitude. The most homes destroyed in Texas by well over an order of magnitude.
And it was frighteningly close. I mean, it's only a few miles from our neighborhood. I mean, like, what, 3 or 4 miles practically?
It's
Windsor Park?
Windsor Park is downtown Austin, right?
No, it's east of 35 along 51st Street to 290.
Oh, sort of. Yeah.
Out to Manor Road.
20 miles away, you could see it.
Okay.
Towering pyrocumulonimbus were created by this storm, but the towering smoke, hit the tropopause, hit the stratosphere. So the point is that there's usually multiple causes to a lot of disasters or catastrophes. If it wasn't for climate change, if it wasn't for the drought on Maui, if it wasn't for the 2011 drought, that was when we set our new drought of record in Central Texas, in Texas. If it wasn't for that, it's likely, and let me use some scientific terms, plausible that the disaster would not have happened. That's one of the reasons why I say often climate change caused instead of it was likely, or that climate change enhanced it, or there was some percentage, like we were talking about attribution a little while ago. So there's always lots of different things. There's this frightening comparison between our fire here and this fire in Maui that, gosh, that was just horrendous. The deaths in Maui exceeded. I filmed the campfire in Paradise, California, the year after it occurred. That is the hardest thing that I've ever done. I film climate change impacts, but they're to our natural world. Climate change impacts themselves, isolated or natural. They happen every time our climate changes abruptly. But of course, we're causing them now. And it's been, 100,000 years since we've had temperatures like this, et cetera. When it happens to the built environment, it's completely different. And the fires in Maui, the fires in Bastrop County, campfire in Paradise, those are tough. And that is really what we're talking about here. Natural systems disasters are important in the big picture, because that's our Earth systems collapsing and creating these feedback emissions that will run away from us if we're not careful. But immediately we've got death and destruction, and just, the 100, 200 people that died, the thousands and thousands of people whose lives were immeasurably disrupted, destroyed by all of these events. Winter Storm Uri, my wife was having a routine urinary tract infection, self-treating, until the storm created gridlock where nobody could move. Her UTI went septic trying to get her to the emergency room. My truck battery died trying to jump the battery. The hood with 8 inches of snow came down the back of my head, smashed my teeth into the fender. They are still, the wife has long sepsis. She spent 9 days in the hospital, had a blood pressure of 52/44. She spent 36 hours in a makeshift critical care bed because all of the hospital beds in the entire Austin region were full from COVID and from ice injuries. So the impacts to the built environment, and I need to stop talking and give other people a chance. Are there any questions about that? That's just.
Well, I think, the thing you said that really, caught me was this sense that natural disasters are usually not natural.
Yeah.
So that even when anthropogenic climate change may not be the cause, then it's something else that, it's land management or fuel management or, whatever it might be in the case of these fires. We had a similar situation with the Canadian wildfires, earlier in the summer that produced terrible air quality across the Northeast and central US primarily, and even parts of the West. What caused the fire? Well, you had a really large ridge, much like the one that's covering the central US right now, causing this big heat wave, right? And so we know that fires happen when the weather is hot and dry. So you can just plot temperature versus precipitation. You find the fire years in the hot, dry corner, right? So it's not surprising then that as our climate tends in some locations toward hotter conditions and drier conditions, that we will get more fire, right? And so is it possible to pull up that attribution graphic that I shared? Because this is a really nice lead into that. Wildfire has a very peculiar location on this figure. Okay, so
what does this graph mean? I saw it for a minute before. It's got a lot in it.
Yeah, so let me take a minute to explain it. So along the x-axis, we're measuring how well we understand the likely influence of warming on that type of an event in general. So for example, you see the things that are the furthest to the right on this are extreme cold and extreme heat. What that means is that we're pretty certain about our understanding that as the world warms, we're going to get less extreme cold and more extreme heat, right? That's pretty much a no-brainer, right? But if you go down more toward the origin on this figure, what you see are things like severe convective storms. And what that means is that we don't have a good understanding of how large-scale warming influences these events generally. Now,
is a severe convective storm a tornado or what?
Yeah, tornado, hailstorm, those kinds of things. And part of that is because these are really rare events, as all extremes are. But, trying to understand the relationship between climate change and tornadoes is pretty tough. We just don't have great data. They're really rare events. The data observations have changed over time. So there's lots of problems there. But as you go kind of toward the middle, look at something like extreme rainfall. So extreme rainfall is there because we have a pretty good understanding. In other words, we know that as the world warms, we're going to have more water vapor in the atmosphere, and then it's going to rain more when it rains. Now, rain isn't just about how much water vapor you have in the atmosphere. It's also about movement of that water vapor to regions of convergence. So this is kind of where my work comes in, is I'm really interested in atmospheric circulation and how circulation moves water vapor around the atmosphere and moves it into these regions of convergence to produce extreme precipitation events. Okay, so that's the x-axis. The y-axis then shows the ability to detect possible influence of warming on an individual event, on a specific event. So instead of saying, how about tropical cyclones there? I lived in Florida during Hurricane Katrina. And, we had a lot of people coming from New Orleans that were kind of refugees from that event. And, there were a lot of questions at that time. Katrina was one of the first storms where people were like, is this humans, right? what part of this is humans? It was a big question, and it led to a lot of those initial papers about climate change impacts on tropical cyclones. But notice that tropical cyclones are kind of toward the bottom of the diagram. And what that means is that we don't have the ability currently to attribute an individual event, right? We know that really bad tropical cyclones hit the United States before we had this current effect on the environment, right? But we also know from the work that Carrie Emanuel and others have done that we've already talked about that we do expect theoretically, and now we see it observationally, that we're going to see some changes in the characteristics of tropical cyclones, right? So the point here is that we don't have the ability to equally attribute all types of climate extremes. So for example, when we get a heat wave, right, we can be pretty certain that some part of that is related to climate change, right? I wouldn't go as far as the language that Bruce used, but that's fair. I have to be very careful in terms of making statements about this. I also think, though, in terms of the discourse, we have to be careful about this, especially as scientists, not to lose our credibility. Because if I come out and say every event is 100% climate change, right, then pretty soon I'm just going to be written off as somebody who doesn't understand weather very well, right? Because again, these events are like this heat wave. You've heard it referred to as a heat dome, right? It's a very large ridge, very large area of high pressure, sinking air, no clouds, right? So we have all of the conditions in place for a heat wave. That can happen naturally, but we know that climate change is making these kinds of events even worse. So this is a really important graphic. The things that are kind of toward the lower left, you can think about is, you should probably be kind of cautious when you think about stating a definitive role for humans in one event, like the Maui fire or like the Canadian fires, right? Because we know that there are a number of other factors that are confounding, like dry grasses or those kinds of things, or the lack of forethought by a utility company to shut off power to a region that has extreme winds. These are all factors, and we see this all the time, right? Go back to the Great Chicago Fire. Does anybody know what caused it?
Yeah.
Was it
Bessie
really
the cow?
It was the cow.
Yeah, Bessie the cow kicked over a lantern, right? So we have to remember that there can be numerous causes. Climate change doesn't have to be ignition, but it can make the fire spread faster, right? There's all kinds of aspects to this that we have to think very carefully and very nuanced about if we really want to tease out what the human role is. And so as a scientist, I'm really bothered. I mean, one of the reasons that I went into climate science is because I really don't like misinformation. I like fighting misinformation. And what that also means for me is that when I hear things overstated, I also have a tendency to want to say, well, hold on, that we don't know that. And so I think we have to be really honest about what we know and what we don't know in order to be believable. And I think, again, that's just kind of a function of being a scientist.
I appreciate that as we're preparing to close the show. Time is just flying. I can't believe that it's almost 8 o'clock. But we have a couple questions from viewers that I'm not exactly sure I'm following them. So I do want to put them in the mix and get answers from them before we kind of seek closing thoughts of any sort from both of our panelists. Both of these are from Anthony DeVere. I hope I said that right. One, he said, I'll just directly quote, "Do you think cyclones are supposed to clean the upper atmosphere?" And the other one, he's asking how long some of these effects last, and are people prepared for this? So your thoughts, gentlemen?
No, Justin, you know about cyclones cleaning the upper atmosphere?
I've never heard that. I'm not sure where that comes from.
I think you could get cleaning from a tropical cyclone from just washing of the troposphere.
Well, yeah, I mean, so, once you get into the stratosphere, the precipitation processes are generally below you. If you're thinking about like raining out the atmosphere, then, in the troposphere, absolutely.
What was that other one?
The stratosphere is going to be kind of unaffected.
Yeah.
The other one was about how long these effects are, and are people prepared? And maybe that's an easy
For these extreme weather events. So
Until we restore our climate back to its original warmth. And no, we're not prepared. Justin?
Yeah.
Yes, I would say that we are currently experiencing somewhere between 1 and 1.5 degrees of warming above pre-industrial levels. These are the extremes that we're seeing at that level of warming. Okay. Now, we're not going to stop warming until we hit net zero. Okay. That's when the warming will stop, right? It'll just go flat. You know, with natural variability still in there. We're still going to have El Nino and La Nina. But if we really want to level off the warming, we have to get to net zero.
meaning we create no more greenhouse gases.
Well, it
at
means
all,
that there's
basically.
a balance between what we emit and what we remove. So it invokes carbon dioxide removal technologies that are, as of yet, just not proven at scale. So
we got time. We'll talk about that.
So we're definitely not prepared to stop this.
we're
at
not
this point.
prepared, and every increment of warming. So if we warm 1.6, it'll be worse than 1.5. If we warm 1.7, it'll be worse than 1.6.
Non-linear.
That's right, and non-linearly in many cases. So every increment of warming matters.
And isn't there this truth that there's a certain amount of warming that's already built into the system that's coming, that you know, if you look at it like a giant wheel turning, that it's, you know, we're here and it's over here and it's coming this way, and it's preloaded now for a certain amount of, I'd say I've seen estimates that there's another degree Celsius increase that's already preloaded into that.
That was actually that was a very common idea, this idea of committed warming a decade ago. Now we actually know that that's not the case. That really, once we get to net zero, things will not continue to warm.
There's
now,
still a lot of controversy about that.
There is, but there are certainly other parts of the system where we know that we'll continue to see impacts. So for example, we're going to have sea level rise for at least 500 years. Probably longer than
unless
that.
we restore our climate.
Exactly, unless we draw down what we've already admitted.
Back, and we're not going to get, I mean, we'll still have some sea level rise, but we can actually reduce sea level rise a little bit, because if we cool our oceans, half of sea level rise has been caused by expansion of warm ocean waters. And just good news, the processes to remove carbon dioxide from the atmosphere have been around for 100 years. One of them, the one I like the best, is cryodistillation. It takes air and compresses it very much, and then it lets it through an orifice, and it expands and it condenses like water vapor in a cloud, and you can literally condense the carbon dioxide out of it. That process was developed by a guy named Lind in the 1870s, so that he could, it was the refrigeration process. It was discovered or invented and used to allow for beer to be brewed in the summer months in Bavaria, where they had a prohibition against brewing beer in the summer because it got these warm weather bacteria that made it taste bad. So one of the most important, or one of the processes for removing carbon dioxide from the atmosphere, is over 100 years old, and through beer we might be able to save the planet.
Well, at least there's some hope.
There actually is some hope. There is some. If I can share,
you have to drink more beer.
Please.
Is that the answer?
Okay, so here's the good thing. The worst climate projections that we thought of a decade ago are probably off the table now. That's the good news. And the reason that that's happened is because coal has gone away faster than expected. So that's not necessarily, I mean, it's a victory, but we're replacing it with natural gas most of the time, which is also a fossil fuel, but it burns a lot cleaner. And so what that means is that what we really thought of as being the worst case scenarios, like 4 or 5 degrees of warming at the global scale this century. I mean, degrees C, big degrees, right? So, those kinds of things being largely off the table, most likely, putting us maybe in a 3.5 degree worst case, which is still terrible. But it's much better than what we thought were the worst case scenarios a decade ago.
Well,
That's good news.
Can I ask a question there? I've seen some very dramatic presentations when people say what 3.5 degrees might look like. Can you say with any confidence what something like that might look like?
Well, I think it means different things for different people. And one of the things that we have to remember is that, if you have a 3.5 degree warming world, in fact, let's not even go that extreme. Let's say we have a 2 degree warming world. What does the map look like? Well, one thing that many people probably aren't aware of is that the land areas are warming more than 2 degrees. The land will warm more than the oceans, right? And then also we have Arctic amplification, which means that the high latitudes in the northern hemisphere are going to warm more than other areas. So 3.5 degrees at the global scale, right? It might look like, 6 degrees at the North Pole, right? And less than that in some other places, particularly maybe over some of the oceanic areas. But the impacts of that would be, not fun to think about.
Well, I guess
just in terms of human suffering, I mean, it's not a good outcome. Yeah.
I mean, I've heard things like food insecurity, such extreme weather events that people potentially are dying, by the millions, things of that nature. I don't want to over dramatize here, but I mean.
Sure. I will say this. I don't believe that there's any scenario from a reasonable underlying storyline, right? So, if you think about like how population grows, how technology changes, how much we adopt renewables, we can produce all kinds of possible futures. Sure. I'm not aware of any of those futures that produce large human die-off in the next few hundred years. I don't see that. But I don't think I don't think we should use that as the marker of concern, right? There's already a tremendous amount of suffering happening because of climate change, even at the level that we're experiencing today. And so I think the way to think about this is that suffering is likely to be compounded at higher levels of warming. But, in terms of like extreme heat, I've seen one paper that was really convincing about the end of this century in the area around the Red Sea. The Red Sea is really shallow. You get high levels of evaporation. It's very hot there. So within this few kilometer strip along the Red Sea, you can get heat index values of 145 or something, right? And so under those conditions, a healthy adult can't be outdoors for more than a few hours or they will die. But these are papers that are looking at possible futures at the end of this century under strong greenhouse gas emissions. So now the qualifier there is that doesn't mean it won't affect labor productivity. Someone in my neighborhood yesterday was having a roof put on and the heat index was 115, right? The dew point was 81 Fahrenheit yesterday. And we will see impacts on things like labor productivity, even if we don't see people falling over and dying directly from the heat.
So we're into a few bonus minutes here. But one thing
I want to add one thing.
Go ahead, Bruce.
It's about tipping, climate tipping, which is basically Earth system collapse responses. Tipping was not supposed to happen until the latter part of the century under business as usual, but more and more publishing is showing that tipping has been activated. Now, tipping in the latter half of the century is the point of no return. That's when it becomes irreversible and we get these feedback emissions that dwarf humankind's emissions. The deal is that once an Earth system collapse begins, and we were seeing them all around us, that it does not self-restore. So our further warming scenarios, and Justin, you talked about scenarios and storylines a minute ago, those don't include tipping activation that does not self-restore unless the thing that caused the collapse to begin is removed. And this is relatively new science. Science is very slow. IPCC is a 6 to 7 year cycle, and individual findings themselves are many years to a decade to collect enough data and get it published. But there are a number of tipping papers that are out that says that it's active now. And we've got to really significantly be concerned about further warming scenarios, because if tipping is active, if these collapses are active tipping, that these are really collapses that are happening to our forest, to our ice sheets, to the Atlantic meridional overturning circulation, basically what is known as the Gulf Stream. Those are very, very serious, because once started, they do not self-restore. That's the thing with the collapse. So,
Yeah. Mm-hmm.
so
And what
that's
do you
the
see
deal.
as but what do you see as the impact to humankind? I mean, we hear like Extinction Rebellion people put out just really violent, dramatic, calamitous results, and then I've been to a presentation at UT where a climate scientist with Martin not that long ago, where she basically said, yeah, 4 degrees, you might see some food instability. I mean, right now, growing tomatoes on my back porch, boy, they are struggling. They are, and usually they struggle in the summer anyway. But what happens to farms? What happens to food production? Bruce?
Well, that is not tipping.
No,
Those
understood.
are old, slow, lethargic, poorly responding models that don't respond well, don't have good feedbacks, and they don't do extremes very well. And that is the new thing, that we've got these extremes that are not well represented in the models. And it's a wild card, but it looks, I mean, from my standpoint, especially for filming these things across North America, I see these collapses happening all the time. And I get into these conversations all the time with scientists. Now, again, I'm an applied scientist. I'm not a PhD, I'm just a PE. But I can make these judgments. And, I'm fairly well qualified. But it is a big deal. And the thing is, it's not in the scenarios. And that is the big deal. And Justin, can you say something about the scenarios and about the unknowns associated with tipping, because they're not in the scenarios?
Of course. So, when we're talking about tipping points in the climate system, the way I would encourage people to think about it is that there's not one, there's many. There's tipping points in lots of different parts of the climate system. So just looking at the AMOC example that was looked at a few minutes ago, there was a story that was pulled up. So that's the Atlantic meridional overturning circulation. It's the oceanic conveyor belt circulation, if you will, whereby we have water sinking in the North Atlantic, and it goes actually all the way into the Southern Ocean and comes up somewhere, I think near India or something. But there's all of this movement of water in the ocean across hemispheres, across depths, and much of that hinges on the formation of this deep water in the North Atlantic Ocean. We have some indication that there's been some slowing in that, and that's a concern. Now, why would it be why would that be slowing? Because when you get fresh meltwater off of Greenland, right, it decreases the density of the ocean water in that area. And so the melt signal from Greenland is actually thought to be a culprit in the slowdown of that overturning circulation. Now, I think at this point, there is still a lot to learn about what's going on there. And also, I would correct just one thing that was said. The Gulf Stream and the AMOC are not the same thing. The Gulf Stream, yeah, so the Gulf Stream is the part that just occurs along the east coast of the US, and it's a very warm current. But the Gulf Stream will exist without the AMOC. In fact, there are papers published a long time ago. You get a Gulf Stream on a rotating planet. That's all you need. You need the continent and a rotating planet, you're going to get the Gulf Stream, right? We always get water flowing from south to north along the western edges of the ocean basins and from north to south along the eastern edges. Yeah, so here's a very simplified version of the sort of what we call the conveyor belt, right? And so you can see there in the North Atlantic, you have warm water that moves to the north and then expels some of its heat to the atmosphere and then sinks into the deep ocean. That current that you're looking at there is the reason that you can go about 10 degrees north in Europe and be at the same temperature as you would be 10 degrees further south in the US. So if you look at like New York and London in January, they're about the same temperature. But London is about 10 degrees north of New York. And that's because the ocean circulation in the North Atlantic delivers a tremendous amount of heat. So if we want to take a look back in time in Earth history, one of the things that happened as the last glaciation was ending is that we had a large ice sheet over North America. And as it retreated to the north, it formed a large glacial lake in what's now Hudson Bay, right, like eastern Canada. And at some point, it's thought that that fresh water spilled out into the North Atlantic and disrupted the Atlantic meridional overturning circulation.
Wow.
That actually produced a period that you might have heard of. It's called the Younger Dryas. The Younger Dryas period was it was a pause in the last deglaciation, where ice sheets that were retreating in Europe, the AMOC shut down and they started advancing again. It did take a little time, but eventually the AMOC did reinstate the North Atlantic circulation, got going again, and then the ice sheet retreat continued.
But so
we
at
know
first
that
this interruption really did freeze Europe.
it did. Yes. And so actually, if you shut down the Atlantic meridional overturning circulation, the first impact that you would see is that Europe would get pretty cold relative to what it is now. So there's all kinds of interesting, that's not really what you would think of in a warming world, but that actually could be a consequence of a slowdown of the Atlantic meridional overturning circulation, because you won't be delivering that heat to the atmosphere that then warms Europe.
And almost all of the rest of the world will continue to warm.
Of course they will.
But except for Northern Europe and maybe Central Europe.
In fact, you can even see that if you look at some of the recent maps of annual climate anomalies, there's a little dark spot. Sometimes it's the only area on the map that wasn't above average.
The warming hole.
There's a little bit of a hole south of Greenland that's probably a meltwater signal, where you have cold water cooling the ocean and then cooling the atmosphere. So it's a large-scale warming causing a small-scale cooling.
Wasn't there
It's amazing.
this age that occurred in like 1300 in Europe?
Well, so there's the Little Ice Age, which people refer to a lot, and a lot of what you might call lukewarmers. They'll say things about, for example, the little ice that we're emerging from the Little Ice Age. That what we're experiencing is natural. We're on the rebound from this cold event. There's kind of mixed evidence about whether the Little Ice Age was really a European event or a global event or a hemispheric event. And there's quite a bit of disagreement about that, frankly.
All of these things come from data. One of the things that we like to do is to look at questions of how people can actually participate in helping some of these things get better. One thing that we learned in preparing for this show was that there is on measuring weather events, there's something that people can participate in. And I understand, Dr. Schoof, that you are well involved in this. Can you explain CocoRoss to our viewers before we go, and what their participation would do?
Sure. I'm actually delighted to give a plug for CocoRoss. So I've been an observer for about 10 years or so. And
an observer, what is this?
So CocoRoss is a citizen science initiative. And so the idea is, if you have some interest in weather, like I really love extreme rainfall. I'm an extreme rainfall nut. But there are other people that are just kind of interested in tracking the weather, watching the weather, and so forth. So if that's you, here's an opportunity to get involved. You can order a rain gauge, and you can order it from Weather Your Way. There's details here on how to do that. But the idea is that you put this rain gauge out on your property and then you report each morning. So for example, I have my rain gauge mounted on the mailbox in front of my house. So every morning when I leave the house, I stop at the rain gauge, I check my measurement, I get out my phone, I open the app, and I put in the amount. It's so easy to do. And so why do it? Well, it feels good to help, but I think importantly, this data is used for hydrometeorological prediction. So in the area I live pretty close to the Mississippi River. I also live fairly close to the Ohio River. So when we think about what's going to happen on those rivers after a large event, after a large rain event, we really need better information than we have from the existing station network. CocoRAS data is actually relayed to the Hydrometeorological Prediction Center, which then uses it to forecast things like flood crest and so on. So it's a really important way to make a difference. It could be involved in saving property or life in your neck of the woods at some point. And so I think it's worth doing. It also produces a lot of great data for scientists like me that are interested in studying extremes. Before CocoRAS, the best that we had was maybe a Doppler radar estimate of what happened. And so what we really see here is that we're getting better and better estimates of how rainfall varies over space and also how extreme it can be. If you look at the CocoRAS map on any given day, you will see extremes that would likely be missed by the existing station network. So today you can see somewhere down there in South Texas, someone reported 6.95 inches.
That was Harold.
You would be amazed at how many days you see a 5 or 6 or a 7-inch total. It's really not all that uncommon when you look across the United States. It's much more common than I would have guessed 10 years ago.
So back before CocoRAS, I guess, the data was mostly coming from, I guess, like mostly weather stations at airports and things like that. And you're saying that just from a few thousand people doing things like put the rain gauge on their mailbox, we are really and truly finding out a lot more about where the rain falls, among other things.
Absolutely. And we're learning more about the structure of weather systems and how the rainfall is distributed, right? This could eventually lead to forecasts that are better. It could lead to, better pinpointing of exactly where the heaviest precipitation might occur with a particular type of system. So it's got lots of great applications. It's also neat, I think, one of the things I've noticed from doing it is that I often find myself looking back through my own record. I wonder what the probability of a wet day is in July here, things like that.
Yeah.
And so, with 10 years of data now, I'm able to start doing some of those things.
This is so interesting. Look, I zoomed right in on the map here, and here's someone's comment. Thanks, Harold, for the much needed rain, but space it out a little next time. Apparently, this is in Robstown.
There's the comments. Yeah.
Yeah,
they've
great.
got 6.51 inches of catch rain here. This is right about near Corpus Christi, and then out here in Corpus, 5.25 inches. And this is today?
Yeah, so this was reported everyone reports a 24-hour total, but you choose your reporting time. I'm a 7 a.m. reporter, but you could report anytime you want to. If you want the data to be used for operational purposes, it's good to get it in early. But 7 o'clock, 8 o'clock, I think is probably fine in most locations. If you want to report later than that, it's still useful to have your data. So I would encourage anyone to do it. And even if you can't report every day, it's okay. Report when you can. It's still helpful.
Did I see this correctly? There were more than 12,000 reports from today?
That's correct. And one of those little zeros in Southern Illinois is mine. And so the other thing to point out here is that, with that big ridge we have over the central US right now that's causing the heat wave that we're experiencing, there's really no rainfall happening in the central part of the country. But look at all those wonderful zeros. All of those observers were conscientious enough to say, even though it didn't rain today, I'm still going to open this app and put in a 0 so that they know that it didn't rain at my location. I just think that's wonderful.
Let's find you, Justin. Where are you?
Go further to the south. I am in Jackson County. So if you go down to, yep, keep going south.
Jefferson, Perry, Williams, Jackson. There you are. Is that
Yes,
you? Or are you
Jackson
in?
County. If you zoom in, I'm in Carbondale. And I am the furthest to the left. Okay.
There
So
he is.
there I am. I am Illinois. I'm Illinois, Jackson County 13, as you can see.
Lucky for
And
some.
you can see I have a 7 a.m. observation. If you
Yep.
look a little bit closer to downtown, you can see I've got a couple of colleagues there that are also reporting. So one of those is one of my colleagues' husband. The other one, I think, is one of our graduate students, although I'm not certain.
Yeah,
But you know, over the
JK31.
years, I have ordered and distributed probably 24 Cocoa Ross gauges. So I've tried to get people involved by giving them a rain gauge, you know, in our community. Because if you look around rural Southern Illinois, you can see that there are still quite a few gaps. So, you know, I'm looking for somebody in Pope County, for example, trying to do what I can. But Cocoa Ross is also connected in many ways to the Weather Service. So, for example, every region has a Cocoa Ross, I don't know what they call them, a supervisor, regional coordinator, something like that. And so if you have any questions, you've got somebody to contact. They're often working at a Weather Service office or somewhere else that would be involved with use of the data.
Well, thank you for explaining that. And just by going to the Cocoa Ross website, we can see how to do it. Is that correct?
Yeah, absolutely. They have training there and everything that you'll need to get involved.
So it's literally COCORAHS.org.
That's right. And if you go back to the Cocoa Ross main page and scroll up to the top, you can see what Cocoa Ross stands for. It's a mouthful: Community Collaborative Rain, Hail, and Snow Network. The whole idea being that we need better measurements of precipitation than those provided by the existing network.
You mean weather guys?
That's right.
Or
Those
weather,
people who
or
didn't show
weather
up on our show.
gals.
Weather people.
But
Weather folks.
Roger that. I'm just want to make one other comment, and then we're way over our time. But you know, this has been a phenomenal conversation, and I hope that our viewers are really getting a lot out of it, because I am. I think that to end this, I just wanted to point out that we have recently learned new terms, weather terms that didn't exist before. The heat dome would be one that we've been talking about, but you know, we had a polar vortex land on Texas that completely took everyone by surprise, and no one had ever heard of a polar vortex until it within, I think, an hour of shutting down the entire state for what could have been 6 months.
4 minutes.
4 minutes. Okay, thank you.
Yeah.
Bruce. Yeah, that's how
Thanks,
close
Bruce.
it was to literally not being able to go to the store, to the gas station and get gas. You know, if you had gas in your car at the time that went down, you might have been able to get out of Texas if you had a full tank. But if you didn't, you would have not been able to get out of this state, and everything would have shut down for, I don't know, a long time. And it was very close, but it's this extreme weather stuff of which we're talking about that has created these new terms. And so polar vortex being one of them, heat dome being another. I don't know if there's any others, but I think we're all learning a lot here just by watching the weather.
They're good terms, you know, that both of those terms existed in the lexicon of meteorologists and atmospheric scientists, right? So, you know, the polar vortex is always there. It's just this kind of wobbly cold blob in the North Pole. It just happened that it made its way down to Texas and therefore was noteworthy, right? But the polar vortex is kind of always there. We call it a heat dome because it's a dome of high pressure, and it produces a lot of heat. So those are both terms that are kind of thrown around in jargon among atmospheric scientists, but they are grounded in actual physical phenomena.
Yeah, atmospheric river was the other one that just
atmospheric river, sure. Which are very important and are leading to a lot of the flooding events that we're seeing, especially along the U.S. West Coast.
Well, yeah, the drought that I think it broke the drought of California. It basically filled up all the reservoirs in a matter of, what was it, like a week? I happened to be in Colorado at the time that was occurring, and the snowfall was unbelievable there. And I actually couldn't get to the airport. I couldn't leave for several days because of that phenomenon. And this summer in Colorado, they've had phenomenal whitewater rafting.
Yes.
Directly related to this atmospheric river. So these extremes can be good to a certain
Absolutely. Degree. Yeah. Growing that snowpack out there helped. Even, Hillary that just impacted California is likely to help a little bit with fire season out there, right? Things won't be as dry as they would have been if that system hadn't come through. So there often are silver linings, but when it comes to climate change, I think we're more likely to lose than win if we don't get busy doing something.
Yeah, one of the things about extra rain in California, where it was designed to burn, is that the year after the good year, it's designed to burn a lot more because there are a lot more fine fuels, and fine fuels are what really carry the big fires.
Well, this has been a fascinating conversation, gentlemen. I really appreciate your time. And I think, hopefully in the future, we will heed the warnings from Bruce specifically to actually take action in our own ways and participate in all the ways that we can. And there's many of them. But gentlemen, maybe we'll return to this subject in a year or so and see where we stand. And hopefully, we'll have some good news to talk about.
This has been an absolute pleasure. I've really enjoyed it, and I would be happy to come back sometime.
Thank you so much for joining us. It's been really fantastic.
You too.
And from the audience, we are getting positives. We got a excellent discussion feedback on the YouTube live broadcast here. So
great.
Well done, folks.
Thank you very much. It's been fun.
Martin,
Right,
shall I shut us down?
Yeah, ladies and gentlemen, thank you for watching this extra special long edition of the Windsor Park Climate Conversation. We'll have another episode in a couple of months. And until then, please keep your weather where you want it. I don't know what that means, but
well, come join the fun of the Windsor Park Climate Conversation and the Climate Committee, where we're working to clean this stuff up.
Thanks.
Good night, everyone.